Hello, welcome to my video on limits. I will be working on a series of videos for differential calculus. Um, the big bulk of differential calculus is working with derivatives, and essentially derivatives are defined as a limit. So we have to begin by understanding limits to get to that topic. So we will begin with that. Today's video we're going to look at limits and one-sided limits. So in order to understand it, we'll look at a variation of Zeno's paradox. This is essentially a race. So we have a rabbit here in red and we have a turtle in green, and we're asked who's going to win the race. They're both starting at 0, they're trying to end the race at 1, and who's going to hit the 1 first. So the restrictions are that the rabbit in red travels half the distance each minute, let's say. So rabbit travels half of the remaining distance. Okay. Let's say per minute. And the turtle, let's say, travels 0.01 millimeter. Let's put the units in kilometers. So this is 1 kilometer, this is 1 kilometer. And the turtle travels 0.01 millimeter per minute. Who's going to win the race? So if the answer seems obvious to you, then you might be thinking about it incorrectly, because after 1 minute, let's say the rabbit is going to be here at 0.5. Let's say the halfway mark is here. Let's put 0.5 kilometers. Okay. And the turtle, after 1 minute, is going to be at 0.01. Let's say over here, 0.01 millimeters. After 2 minutes, the rabbit is going to be here. It's going to travel half the remaining distance. So the remaining distance between 0.5 and 1 is, let's say, 0.5, and half of that 0.25, giving us 0.75 kilometers. So he's 3/4 of the way there already after 2 minutes. Okay, I'm gonna put a little 2 on, put a 1 here. Whereas the turtle after 2 minutes is gonna be over here. Okay. But the reason why this is called a paradox, and although it looks like the rabbit's clearly ahead and he's gonna win the race, he's always traveling half the remaining distance. So after 0.75, whatever the value is between 1 and 0.75 divided by 2, what you have to realize is that half the remaining distance, although it gets really close to the finish line, he's always going to be traveling half the remaining distance, which means he's never actually going to attain the finish line. He's going to come very close to it, but he's never going to hit the 1 kilometer mark, because he's always going half the distance. So even though it's getting very small, he never finishes. So although the turtle's going to take a very long time to get there, he's actually eventually, after maybe days, he's going to attain the 1 kilometer mark. So the answer to this question, who wins the race, is actually the turtle. Okay. And this is a variation of Zeno's paradox. And this introduces us to limits. So let's look at a formal definition and look at how to calculate values. So when we're talking about limits, we're talking about what's happening as we approach a value. Okay, so to define a limit, we say that f of x approaches the limit L as x approaches the constant a. And we write it this way. We write lim, limit, as x approaches a, x approaches some number, of f of x is equal to some limit L. So here I wrote a and L are elements of the real numbers. They're just constants. And another notation you can use is f of x tends to L as x tends to a. typically we use this notation here. Okay. Yeah, so let's take a look at an example to see exactly what this means. So in this example over here, we have the function f of x equals 1 over x. And we're asked to find the limit as x approaches 2 of this function here. So what we're saying is, as we get close to 2, this value on the graph, what's the y value that we're approaching? Well, as we get close to 2, we hit this point over here, which is approaching this value here on the y-axis, which is a half. So when we're saying the limit as x approaches 2, as we get close to 2, we're hitting the function at this black point over here, and that's associated to the y value of 1/2. So the limit as x approaches 2 of f of x is a half. Okay. Let's look at another example. Okay, so in this example here, we have this function over here. It's discontinuous at the value 5. So we have a point that's removed, it's placed over here, and then it continues over here. And the question is asking us to find the limit as x approaches 5 of this function. So I'll give you a moment to pause the video, try to solve it on your own. So at this stage here, if you're thinking the answer was 1, that's incorrect. The answer is 2. So let's see why. When we're talking about limits, what we are asking ourselves are, what's happening, or what's the y value associated to this function as x approaches 5, as we get close to the value of 5? What's the y value that we're getting? We don't care what's happening at 5. Exactly at 5, we know that the y value hits 1. But what's happening as we get close to 5? So think of it as 5.1 or 4.99. As you get close to 5, we're hitting the function up here. From the left and the right, it's coming up here. So at 5, the value's at 1, but when we take the limit as x approaches 5, as we get close to 5, it's actually hitting here at 2. Think of this as the example we saw earlier with the rabbit. The rabbit, as it was finishing the race, it was approaching a value of 1. It never hit the value of 1, but it was approaching it. And that's what we care about when we talk about limits. Okay. So in this example here, the limit as x approaches 5 of this function here is 2. Okay, so now we're going to look at one-sided limits. So just quickly, we have left-sided limits and right-sided limits. Essentially, left-sided limits, the notation we use is the limit as x approaches a. And this is a superscript with a negative. So we have a negative of f of x equals a, opposed to just having a here. And right-sided limits, it's the same idea, limit as x approaches a with a superscript with a positive sign of f of x equals a. So what this is saying is a to the negative, what we're talking about is on our number line, if this value is a, when we say a negative, we're saying slightly to the left of a. So a negative is a number that's extremely close to a, but slightly to the left. Whereas a positive is, again, a value that's very close to a, but slightly to the right, to the positive side of a. So essentially, if a is 2, then 2 negative and 2 positive, what you're really thinking of is the value that's very close to 2, but slightly to the left of it, which is essentially 1.9999 repeating. And a number that's very close to 2, but to the positive side, you're thinking of the value 2.00, a bunch of zeros, and ending with a 1. So something that's really close to these values, but one that's slightly to the right of it, and one that's slightly to the left. Okay, so let's take a look at an example. In this example here, we have our function which is in green, sort of a quadratic that stops here at the x value of 3, y value of 2. It breaks, we have a piece over here at 1, just one single point, and then after it continues as of 3 as a straight line. So this is our function, and it's asking us to find the limit as x approaches 3 from the left side of f of x. So again, you could pause the video, try this on your own, and then compare your answers with mine. So the limit as x approaches 3 from the left side, we're thinking of the value 2.99. If we go slightly to the left of 3, this value here is 3. You're thinking about here. The value you're hitting is up here. So the y value associated with 3 to the left, slightly to the left of it, it's approaching a y value of 2. So the left-sided limit would be 2. Okay. The limit as x approaches 3 from the positive side, so slightly to the right of 3, of this function here in green, is slightly to the right of 3 would be here. The value you're approaching is, as you get closer to 3, the y value associated to this value here is 0. So the right-sided limit of this function at 3 is 0. And then lastly, we have f of 3. So you have to understand the difference between limits, and then if you see this notation. This notation here, there's no limit sign in front, it's just saying what's happening exactly at 3. When we talk about limits, as I mentioned earlier, it's as we approach the value of 3, from the left and from the right. Whereas here, f of 3 is saying what's happening exactly at 3. Well, exactly at 3, it's defined at this point here, the solid dot, which appears at a y value of 1. So f at 3 is 1. Yeah, so make sure you understand the difference between limits of a function versus functions defined at an exact point. Okay, so when we talk about limits, it's as we approach values, what's happening to the y values as we approach a certain x value, whereas f of 3 is what's happening exactly at the value 3. Okay, so now we're going to look at a very important notion, the existence of a limit. So in order for a limit to exist, the left-sided limit and the right-sided limit must be equal. So in math, the way we could write it is that the limit as x approaches a of f of x equals L. That's just the regular limit. It's equal to L. If and only if the left-sided limit, the limit as x approaches a from the negative side, the left side of f of x equals L, and the limit as x approaches a from the positive side, or the right side, of f of x equals that same L. Okay, so if the left-sided limit and the right-sided limit give us the same value, then we state that the limit exists. Okay, this is an important notion. Let's take a look at an example. So here, if we are looking for the limit as x approaches 6 of this function here, the function in block. So we essentially have a straight line with a hole at 6, the dot is placed here, and then it continues along the same path. We're taking the limit as x approaches 6 of f of x. We want to know this. Well, in order to see if this limit exists, what you have to do is check the left-sided limit and the right-sided limit. If the left-sided limit and the right-sided limit give us the same value, then we could state that the limit as x approaches 6 of this function exists and goes to the same limit. So let's write it on this side. If we look to the left of it, so if we consider the limit as x approaches 6 from the left side, with a little superscript, the negative sign of f of x, this value, 6 to the negative side, so we should be thinking of the value, let's say 5.99, very close to 6, but slightly to the left of it. This value is approaching the open dot, which is at 4. Okay. So the limit as x approaches 6 from the negative side of x is 4. And the limit as x approaches 6 from the right side So again, 6 from the right side, we're thinking of a number that's slightly bigger than 6, so like 6.01. And it is also approaching the same value of 4. Since the left-sided limit and the right-sided limit go to the same value, that means the limit as x approaches 6 of f of x is equal to 4. It exists and it's equal to 4. Okay. So again, we don't care about what's happening at 6. The fact that the point may not even be defined, it doesn't have to be there, doesn't affect the limit. Okay, so in this example here, we have a function which resembles something called the Heaviside function. And what it is just essentially a straight line at -1. So for all x values smaller than 0, it's just a straight line at -1. It's open dot at -1, open dot at +1, but solid at 0. So the point at 0 is defined at 0. And then after, for all the positive x values, the function is just the straight line at 1. So this is the function that we're given. And it's asking us to find the limit as x approaches 0 from the left side, the limit as x approaches 0 from the right side, f of 0, and the limit as x approaches 0 of f of x. So I'll give you a couple of seconds to pause the video, think about this question, and find your own solutions. And let's solve this together. So I strongly encourage you guys to try the problems on your own. Okay, make sure you're not just following and watching the video. Make sure you're practicing and not just watching someone else do math. So the limit as x approaches 0 from the left side of f of x is to the left of 0. So let's say negative 0.01. And that's going to give us a value of negative 1. It's going to come and hit the function down here. The value we're approaching is negative 1 as we approach 0 from the left side. As we approach 0 from the right side, so positive 0.01, it's going to hit the function up here at positive 1. Okay. F of 0, so where is it defined exactly at 0? Well, that's the solid dot. That gives us 0. And the limit as x approaches 0 of f of x dne does not exist. This solution doesn't exist because the limit as x approaches 0 of f of x only exists if the left-sided limit and the right-sided limit equals the same value. In this case here we have negative 1, here we have positive 1. They're not the same values, so the limit at 0 does not exist. This is very important. This is what we just saw. It's a counterexample to what we just saw before. Okay, so since the left-sided limit and the right-sided limit do not give the same value, the limit at that value, at 0, does not exist. Okay, so this is a great example to see if you truly understand the idea of the notion of a limit, one-sided limit, and what's happening at a defined point. So we have this function over here, which is essentially a semicircle. Starting at negative 1, it goes up here to 1, but at 1 it's an open dot going to 0, and then the semicircle closes up until the x value of 1, but it's an open dot here. And then continues up here at 3, it's a straight line down going to 3 as well on the x. And at 3 it's defined at the point 1, and then continues up here at 2 with an open dot just going off to infinity. So we're asked to find here the limit as x approaches 0 from the left side of f of x. Again, pause the video, try this on your own, and see if your answers matches mine. So the answer for the limit as x approaches 0 from the left side of f of x, what we get is, what we're looking at is 0, a bit to the left of 0, we're looking over here, and if we go hit the function, it's approaching a y value of 1. So the answer for this guy is 1. The limit as x approaches 0 from the positive side of f of x, so the positive side is here 0, a bit to the right of 0. Again, from the right side, the function is approaching a value of 1. Limit as x approaches 0 of f of x, since the left-sided limit and the right-sided limit both give us the same value, this gives us the same value as well. So this is 1, the limit exists, and it's at 1. And f of 0, it's defined at the point 0, because it's at the origin. Okay. E. Limit as x approaches 1 from the left side. So as we approach 1 from the left side, what we're doing is we're looking here at a value that's smaller than 1, so like 0.99. The function is going towards on the y value of 0. The limit as x approaches 1 from the positive side. From the positive side of 1, we're hitting the function all the way up here. It's approaching a y value of 3. Limit as x approaches 1 of the function. Since the left-sided limit and the right-sided limit give us different values, they're not the same. This does not exist. The limit doesn't exist because the left-sided and right-sided limit give different values, but at 1 it's defined at, since it's a solid dot, it's defined at 3. Okay. We have the limit as x approaches 3 of f of x. So what's happening here, it didn't ask for the left-sided and the right-sided limit, but you have to check that anyways. From the left, notice that it goes to 0, but from the right it's going to 2. Since the left-sided limit and the right-sided limit give us different values, the limit does not exist at 3. But is the point defined at 3? Well, if you look at 3, it's a solid dot here, which is associated to a y value of 1. And these are the answers.